In this video, we're excited to present our latest research at the CVPR conference, PI3D, Efficient Text-to-3D Generation with Pseudo-Image Diffusion. Our poster session is scheduled from 10:30 to 12 Urs on Friday, June 21st. We're here to discuss our innovative approach to text-to-3D generation, a field that's rapidly evolving with the advent of AI. Text-to-3D generation has been a challenging task in the field of computer vision. Some pioneering methods rely on 2D priors and techniques such as score distillation sampling. However, they often fall short due to their time-consuming nature and lack of 3D prior knowledge, leading to what we call the Janus problem. On the other hand, we have 3D prior-based methods such as Point-E, S-Diffusion, Shap-E, and others that incorporate point cloud diffusion, 3D voxel diffusion, and NeRF diffusion. While these methods bring us closer to realistic 3D generation, they still suffer from degraded 3D quality due to the limited quality of available 3D datasets. Diffusion models are incredibly powerful, but they require vast amounts of data to perform optimally. For instance, we have the 2D text-image dataset Leon 5B, with approximately billions of samples. In contrast, the 3D text object dataset Objaverse has only nearly 1 million samples, and even some of those are of lower quality. The question we ask is, can we build a generalizable 3D diffusion model when our 3D data doesn't match the scale and quality of image data? The answer lies in combining 2D and 3D datasets to train our 3D diffusion model. The idea starts with a key observation. There is obvious semantic similarity between orthographic projections and triplane features for the same 3D object. We propose to treat triplanes as pseudo-images, where each of the 3 channels converts to an RGB image. This allows us to fine-tune a pre-trained diffusion model using both 3D and 2D data, thus retaining the 2D prior. Let's delve into our method. First, we have per-object depth-aware triplane fitting. This involves creating an axis-aligned visual hull and a 6-channel triplane from multiple view renderings, effectively converting 3D data into a format that can be used by our diffusion model. Next, we adapt the stable diffusion model to work with our pseudo-image diffusion model. This adaptation allows us to leverage the strengths of both 2D and 3D data in generating high-quality 3D outputs. We keep the original architecture and perform several modifications. Firstly, we adapt the original self-attention layer in each block to the self-attention on 6 pseudo-images to build feature interaction across different planes. Then we add a learnable 3D indicator as the global condition to the time embedding to instruct the U-Net to work in triplane diffusion mode. For each denoising step, the pseudo-images are encoded as latent triplanes by the frozen VAE encoder. A crucial aspect of our approach is the hybrid training strategy. Fine-tuning the model solely on the 3D dataset can lead to quality degradation. To maintain the original 2D prior, we fine-tune the model with both 2D and 3D data, ensuring a balance between the two. In the ablation study, we found that replacing the training batch with text-image pairs with the probability of 50% leads to best quality in 3D generation. Additionally, we incorporate a lightweight SDS refinement step in our method. This step further enhances the quality of our generated 3D models. Thanks to the good initialization of the sampling stage, the subsequent refinement can be done with significantly fewer steps and takes only around 3 minutes to produce satisfying results. Let's take a look at the results. Here, we present a visual comparison of our method against existing methods, Point-E and Shap-E. The improvement in quality and efficiency is evident. Moving on to quantitative comparisons, our method shows promising results, outperforming other state-of-the-art techniques in terms of text alignment. We also demonstrate the integration of our PI3D model with Deep Floyd IF, showcasing how our method can be applied to generate 3D models within approximately 3 minutes. We also explore the integration of PI3D with other forms of 2D guidance, further enhancing the versatility and applicability of our approach. With a generalizable 3D prior, PI3D can significantly reduce the number of iterations required to achieve plausible results. Finally, we present several examples to illustrate the generation diversity of our method. In conclusion, PI3D offers an efficient and effective approach to text-to-3D generation by leveraging pseudo-image diffusion. We look forward to discussing our work with you during the poster session on Friday, June 21st. Thank you for your attention.